Welcome to another video on the iGetChem channel where we help you learn chemistry the easy way by showing you how to solve problems. This is another video on the harmonic oscillator. We have posted a video on the wave functions and eigenenergies of the harmonic oscillator and in general what those wave functions and eigenenergies actually mean for the quantum mechanics of the harmonic oscillator. So it might be a good idea to check out that video first before you look at this one. But this one is a follow-up, essentially using the results derived in that problem for the harmonic oscillator wave functions to look at the uncertainty relationship between the position measurement operator and the momentum measurement operator. So let's go over the problem and we can get right to the solution. A, evaluate the expectation value for x squared, x being the position measurement for the harmonic oscillator, and from this obtain delta x, which is the standard deviation of the x measurement. Part B, evaluate p squared expectation and the square of the expectation of p for the harmonic oscillator and calculate the uncertainty in the momentum measurement. And finally, part C is to use the results from A and B to illustrate the uncertainty relationship for the wave function in the harmonic oscillator. So in the other video on the harmonic oscillator wave functions and eigenenergies, I'll make a link to that at the end of this video. We said that if you have the Schrodinger equation, which is H psi is equal to E psi, H is a combination of two terms. Basically, there is a translational energy operator and a potential energy operator. So the Schrodinger equation can be also written like that. We know the translational energy operator for a one-dimensional system is p squared over 2m. And in this case, since we are talking about only one dimension, I'm just going to forget the subscript px. So p is in the x dimension, which is the only dimension in the system. And for the harmonic oscillator, so this is for the harmonic oscillator, then this potential energy operator is just a form of the potential energy, which for the harmonic oscillator is 1/2 m omega squared x squared. So I'm going to see if I can draw a function of the potential for the potential energy. So again, this is 1/2 m omega squared x squared. So what that really looks like is simply a parabola. So basically it looks like that. And the parabola, of course, is symmetric with x because of this x squared right there. So, so what we can then do, if we take the Schrodinger equation with those two terms and write it down explicitly for the harmonic oscillator, then we will get these two terms. In quantum mechanics, p squared over 2m will go to h bar squared over 2m d squared dx squared. So that is the essentially the translational energy operator. And then the second term, that is here, so there's a plus right there. And then the second term is this other term right there, 1/2 m omega squared. And this whole thing is then operated on the wave function psi, which here is a function of x. So this is psi of x. And then on the right side, we have an eigenenergy E. Let me use a different color just so that it looks different from the other one. So the eigenenergy right there. So if you have looked at the solution that we have provided in the other video concerning the harmonic oscillator wave functions, you can see that you can use scaling to actually scale away some of these coefficients. So you see this coefficient and that coefficient. If you use an appropriate scaling, and what I mean by that is there is a transformation of coordinate that you can employ that would allow you to essentially rewrite this equation in a much simpler way. So instead of this being d squared dx squared multiplied by minus h bar squared over 2m, this just becomes minus d squared dy squared for the kinetic energy term. And for the potential energy term, this just becomes a y squared. And now this whole thing then operates on psi, which is now a function of y instead of a function of x. And this is equal to some dimensionless energy multiplied by psi. But psi is now a function of y. So the way you get this to work out is by selecting an appropriate transformation of coordinate. Let me write that down so you know what that involves. Basically, what you want to do is every x that you see, so I guess I'm missing an x squared right there. For every x that you see, you will replace it by y times L. So right here, the transformation of coordinates is x goes to y times L. And L is just some length scale that you have to choose appropriately. And if you choose that length scale appropriately, then the equation, the original Schrodinger equation, will then become the one on the right, where the correspondence is, of course, in addition to this transformation of coordinate, the proper way to write down L, or the proper choice of L, is such that L squared is equal to h bar over m omega. And this dimensionless eigenenergy is equal to the real eigenenergy in that divided by or measured in units of h bar omega over 2. And the dimensionless eigenvalues we have found are basically integers or odd integers, 1, 3, 5, ... Or in general, you can write it as 2n plus 1, where n is the vibrational quantum number, 0, 1, 2, and so forth. So going back to the real energies, then the real energies of the original problem is now equal to the dimensionless energy multiplied by h bar omega over 2. And since the dimensionless energy is 2n plus 1, then the real energy of the harmonic oscillators for each eigenfunction is given by this, this relationship. So basically, solving the equation on the right is essentially going to give you all the solutions for the equation on the left. And the equation on the right is easier to solve because it doesn't have these coefficients anymore, and everything is nice and clean. So what that means is whichever you have on the right, so for example, what you could do is to, for example, measure the expectation value of y. And that, of course, means you will integrate over all values of y, take a wave function, psi of y. The wave functions for the harmonic oscillator are real, but in general, what you need to do is to take one of the psi's and take the complex conjugate of that in case it is complex in value. And then you can then multiply that by the measurement, multiply by another factor of the wave function. And in order to make sure that this is properly normalized, you can just divide by the same integral except without the measurement. So by measurement, I mean that one. So the bottom is exactly the same as the top, except there's no measurement there. So that is y squared. So if you look at that, then of course you can write down the exact same thing on the other side for x squared. So here I can write down the same thing, x squared. So the problem basically asks you to derive x squared, but because these two are essentially equivalent, you can essentially calculate y squared instead of x squared, and that's a bit easier than x squared. So x squared is equal to this. But of course, x squared and y squared are related because of this relationship, right? Because this relationship tells us how to transform y squared to x squared. And so you see x squared is y squared multiplied by L squared. So this is just y squared multiplied by L squared. So after we have y squared, we can just multiply by L squared, and we can get x squared, which is what the problem wants, and this is what L squared is. So let's do that because that's fairly easy. So what we will do is to do that for the first eigenfunction corresponding to quantum number 0. And so the first eigenfunction, which we will call psi 0, is equal to something like this. So there's a constant multiplied by e to the y squared over 2. As we have said, these are called Gaussian functions. I think there are two s's. These are called Gaussian functions, and the constant in front of that is to make sure that the wave functions are properly normalized. But if you do what I'm doing here, that is you always divide by the normalization, then you can essentially remove that coefficient because you are going to normalize it properly. So for the rest of the problem, we are just going to get rid of that. So psi squared is just equal to that. Psi 0 is just equal to that Gaussian. Now, of course, on the left side, psi 0 of x is a bit more complicated, right? It's certainly going to be a function of x, but you can see that because x is equal to y times L, the proper Gaussian is going to be x squared divided by 2L squared. And again, you have a bunch of constants in front. But so we are going to deal with this function on the right because that's just a little easier to work with. And so this is the first eigenfunction. And corresponding to that, the energy of that is equal to 1 in the dimensionless energy. So as we have said, the dimensionless energy is related to the real energy by that relationship. So on the left side, the eigenenergy of that wave function is h bar omega over 2 multiplied by 1, right? So if this is 1, then you just, so let me just erase that so that I don't get confused. So on the right side, certainly the corresponding eigenenergy for that one is just h bar omega over 2. So we have the wave function and we have the eigenenergy in both the original system, the original equation, and the scaled equation. So what we are going to do is to now calculate y squared. So this is a fairly simple calculation because of these Gaussian integrals. So basically what you have is y squared is equal to, now I'm going to put in the Gaussian function, and this is measuring y squared. And these integrals are from minus infinity to plus infinity. So I'm not going to put all of the details in, so you know what I mean. So obviously when you multiply the two Gaussians together, y squared will give you dy, and it's just e to the minus y squared, and there is a factor of y squared. And in the bottom, you see you have the same thing, but without the y squared. So we need to do that integral. So you can actually do that integral fairly easily if instead of taking that Gaussian, you think of it as the integral of e to the minus some alpha times y squared. So let's consider that integral. I'll call that I. So that integral is defined to be that, and that's obviously a function of alpha. So what I could do is to essentially take the derivative of I of alpha, and again this is y from minus infinity to plus infinity. So I can differentiate the integral with respect to this alpha, and if you do that, then the differentiation will commute with the integration. So what you have is basically d alpha of e to the minus alpha y squared. And you can of course do that because the alpha, there's a factor of alpha there. So what you are left with is the derivative of this I integral. So d I alpha d alpha is now equal to the integral over y, and you can easily do that because the derivative of the exponential is the exponential, but then the derivative of the exponent will then bring down a factor of minus y squared. And so you see the derivative of I is basically just this integral. And now that integral is what we have on the top, except for the minus sign, right? So what we have is the integral on top. And so what we then have in the bottom is essentially just the original integral, which is that one. So what we need to do is to just set the alpha equals to 1 for both the derivative and the original integral, and then we will get the right answer. So you can do that, or you can look up the tables for Gaussian integrals, or you can do it on Mathematica. It doesn't make any difference. At the end, you will see that the integral right here will give you 1/2. So that's the result of that y squared. So now we know that that y squared is 1/2. So using that information, we can then go back to the right, because there is a relationship between x squared and y squared, because now that we know what y squared is, we can now go back to the left side and calculate what x squared is. Y squared is 1/2, and L we have up here. So this is L squared. So that is 1/2 multiplied by h bar over m omega. So 1/2 multiplied by h bar over m omega. So that's what x squared is. So that is part of the result we want. for part A, we want the average of x squared, or the expectation value of x squared, and that's it right there. The second one we need is what is the average of x, expectation value of x. Well, that's actually very simple. That's equal to 0. The reason is obvious, because the potential that we have at for this problem is completely symmetric. The harmonic oscillator potential here has this x squared. And because of the symmetry, if you take an average, the average of x is going to be essentially 0, because the potential is completely symmetric if you flip x and minus x. So what that implies is simply the average of x is simply 0. So from this you can then easily calculate the expected value for the variance in the x measurement, which is defined as x squared expectation minus the expectation of x squared, which is really just the square root of this. So square root of 1/2 h bar divided by m omega. Okay, so that is delta x. Now we have to do part B, which is to do the same thing but for delta p. So what you can do is to go and use the definition for what p is from the original Schrodinger equation. So you can go back here, and then you can see that this in the Schrodinger equation stands for p squared over 2m. And so if you want the expectation value for p squared, then what you would do is to take the expectation value for that. So take the expectation value for that, and that is basically equal to minus h bar squared over 2m d dx squared, the expectation value of that. And of course, then you can basically move this around a little bit. So let me see if I can do this right here. So this is basically p squared expectation value on top over 2m must be equal to minus h bar squared over 2m multiplied by the expectation of d squared dx squared. So that's in the original equation. But now in the scaled equation, then that becomes fairly simple, because the only thing I have in this case is just that. So certainly if I write the momentum in terms of y instead of x, then this will just come out to be the expectation value of d squared dy squared with a minus sign. Okay, so what I need to then do in the scaled equation is to just evaluate the expectation value of the double derivative, and we should then be able to calculate what that is, right? So let me do that right here. Again, what we want is d squared dy squared. Let me put a minus sign in front so I know I'm getting this correctly. And so you use that definition again. So you just basically put in dy from minus infinity to infinity, psi star of y, and now this is d squared dx squared psi of y. And again, to properly normalize it, you divide it by the same thing, but no measurement again. Just like that. So again, using the functional form of the first wave function of the Gaussian, you can see that this is just that. Sorry, right in the Gaussian. So e to the minus y squared over 2. And this is d squared dx squared e to the minus y squared over 2. And this is then divided by the same normalization, e to the y squared. Now, so you can do that integral again, just like you do the other integral for y squared, or you can use Mathematica or look up a table. But so of course, what you first need to do is to calculate the double derivative of the of this term. Instead of doing that, we are not going to do that, but there's actually an easier way to actually get that without even having to do the integrals. The reason is actually very simple. You see the equation right here on the right side. This is the equation. So I'm going to take that equation and rewrite it so that we are clear what we are looking at. So this is for the first eigenfunction. If you look at that equation basically tells you it is minus d squared dy squared plus y squared is equal to, for the first eigenfunction, the dimensionless eigenenergy is just 1. So that's just basically on this side equals to psi 0 of y. So that's what this is. So what you can then see is I can multiply on both sides of this equation by another psi or psi star. And now I can integrate that over all values of y dy. So now you can break up the terms, but you can basically see that when I do that, all you're really doing is that you are taking the expectation value of basically the first term, which is that, and then the second term is the expectation value of y squared, which we have already calculated. Now, of course, what that does, what is in here, will basically just give you, so this is just equal to 1. So without doing the integrals up right here, I can already calculate what the expectation value of the double derivative is. Since I know the expectation value for y squared, this one, is just 1/2, then there is no doubt that the expectation value of this is 1/2. So we didn't really have to do this integral. The result is fairly obvious from the Schrodinger equation because we know the dimensionless eigenenergy. So now that we have that, we can then take that and put it in here. So we have this double derivative with respect to y and expectation of that in the scaleless form. And so if you want p squared over 2m in the original units, this is simply just minus h bar squared over 2m. And because x is equal to y times L, this is certainly equal to 1 over L squared, d squared dy squared. And now that we know that is equal to 1/2, then everything becomes pretty easy. So let me now write everything back in. So I'm going to write down p squared over 2m. So p squared over 2m, the expectation value of that, is equal to h bar squared over 2m. I think this minus is already inside. So you see I've already put that here. So there's no minus sign. H bar squared over 2m over L squared. One over L squared. And the expectation value for y is 1/2. So that is in real term what p squared actually is. So now I can basically see that p squared, because the 2m cancels, is basically just h bar squared over L squared times 1/2. Okay, now the last thing is to put back in the value for L squared. So L squared is this, h bar over m omega. So this is h bar squared, h bar, sorry, let me put the square outside, over m omega squared times 1/2. So just making things easier. So there's no squared because L squared is just h bar over m omega. So now canceling out this factor of h bar. So I have one factor of h bar right here. And then the m omega goes up. So this is h bar times m omega. And this is then multiplied by 1/2. So that is what p squared is. And we need to calculate delta p, which is p squared minus p squared, the expectation value of p squared, and the square root of that. So we've got p squared right there, averaged. So the question is, what is this expectation value of p? Well, that's also fairly easy, because the expectation value of p is going to go to 0. The reason, again, is because the potential is symmetric. So the harmonic oscillator potential looks like that. Because it's symmetric, every wave function has as much right-going wave as it has left-going wave. So these standing waves are produced by basically adding up the equal amount of left and right-going waves. So at the end, all the stationary eigenfunctions of the harmonic oscillator, because it's completely symmetric, should have no net momentum. So p is equal to 0. So once we know that, then this is fairly simple. This is just the square root of p squared, and p is this, so it's h bar m omega over 2, and it's the square root of that. Okay, so now we've got both. So we have in this expression the variance of p, or the standard deviation in the measurement of the momentum operator. And then in this expression up here, we have the delta x, which is the standard deviation in the x measurement. So that's 1/2 h bar over m omega. So if we multiply those two together, so again, 1/2 h bar over m omega. That's delta x. And then delta p is h bar m omega over 2 right there. And so clearly the m omega cancels, and you have two factors of h bar but the square root, so just have h bar. You have two factors of 2 but square root, so this is h bar over 2. So finally we got this relationship right there, which is precisely the uncertainty relationship that you expect. So delta x times delta p reflects the product of the uncertainty in the measurement of the position and the momentum of the harmonic oscillator in its ground state, and that is h bar over 2. So that's the end of the problem. But before I stop, let me just say one more thing. You can obviously do this for all the wave functions. The one that we have worked out in this problem is just the ground state. So the only one that we have worked out in this case is for the ground state, which has eigenenergy in the real problem equals to h bar omega over 2. So the question is, if you have if you apply the same calculation to the other eigenvalues, what would you actually get? So to just quickly go through that, remember the way we did the problem is to essentially take p squared over 2m, and the other term is 1/2 m omega squared, the expectation value of x squared, and that is equal to the eigenenergy of the harmonic oscillator in the real energy. So this is 2n plus 1. So for n equals to 0, we have worked that out explicitly for all n. So for all n, this is certainly going to be true. So you see that as n increases, so for the harmonic oscillator, the ground state is n equals to 0, but then the excited states, so the high energy eigenstates are 1, 2, 3, 4, and so forth. And for every term, you will basically see that for every eigenfunction, you basically see that the energy, the total eigenenergy of that wave function is split 50% between the kinetic energy and the potential energy. So both of these will go up as you go to higher and higher eigenenergy. And so what that means is if you calculate delta x and delta p for the higher eigenfunctions, they will also be bigger. So what that means is that for the higher energy eigenstates, the product delta x multiplied by delta p will actually grow. So it's no longer just h bar over 2, it's going to be bigger than that. So what that really means is that the uncertainty measurement, or the uncertainty in the measurement of the position and the momentum in the ground state, this is n equals to 0, is h bar over 2. But for all the excited states, this is actually worse than that. So this is actually greater than h bar over 2. So in fact, the uncertainty principle should really be called the minimum uncertainty principle. It's that delta x times delta p equals to h bar over 2. That's only sort of the minimum you can have. And then for some of the other wave functions, as we have seen for the harmonic oscillator, that uncertainty is going to be actually even bigger than that. Okay, so that is the end of this problem.